outbreak spread across my hometown in a matter of days. No one was prepared for the sudden occurrence of this nature. I had to flee town and make my way across the state to find safety. Along my travels, though, I stumbled upon something that could lead me to the answer. There is a group of people working on something amazing, apparently using what they call machine learning to classify these cells and be able to better understand who has malaria or not. But their last known location was the hills of Moraga. So onward, I continued.
Malaria!
It's everywhere.
Yes, Mr. President. We'll take care of it. Let's go, team.
This is very natural. Man, that machine learning model is taking forever to train.
Yeah, our minority class is really imbalanced.
Yeah, there's a lot of malaria.
Oh my gosh! Who are you people?
We're Team Alpha.
Have you guys heard about the malaria outbreak?
Yeah, we built a machine learning algorithm to identify malaria cells.
Oh my gosh, that's perfect!
We're gonna start training the model.
Is this cancer? Oh my god, malaria!
I heard you have malaria. Don't die, Jordan! Oh no!
Time to kick in the overgear. Oh my god, we fit the model.
Hi, Ahmed. This is Nick from Team Alpha. I am just going to be sharing my cannot see. Okay. Sharing my screen here and going over my portion of the code. So I decided to use a random forest model, and the data set that we're working with is the malaria data set. And so here, I'm just going to go over my code here. This is the beginning part where I'm generating the paths to the files, the directory. It's a directory which contains two directories of 13,779 images of infected and uninfected cells. So I'm just importing the data here. And then in this section, I'm creating a data frame and labeling each cell as infected or infected or not infected. And then here I'm splitting the data. I'm using a testing size of 30% and a training size of 70%. And then in this section, I am, because all the images are different dimensions, I needed to find out kind of what is the average dimension to standardize them to. And I looked up some kind of cool parallel processing techniques to run this. So as you can see, the minimum dimensions are 40 by 46 by 3. Average is 132, 132 by 3. There's the median, there's the max. So based on that, I decided to resize the images to 125 by 125 dimensions. And yeah, so this part, this is a function that does the resizing of the images. And again, I used a threading or a parallel processing technique to speed this up and do it quickly. So you can see that the end result, this would be my training set, is 19,290 by 125, by 125, and the test is 8,268. So yeah. And then I scaled the images for processing, and I wanted to visualize some of the cells. So here's, I just plotted, this is 20 cells, labeling them infected versus non-infected. So you can clearly see, like, here's a non-infected cell. There's a lot of infected cells, and you can see the differences in the cells and what we're going to be trying to capture, looking for these kind of discolorations. And then some more pre-processing. I flattened and reshaped the data for the training and testing set. And I decided to use a random forest ensemble classifier with 100 decision trees. And I fit the model here and then predicted. And I did a classification report. So you can see that the precision for model is 79% for predicting infected, and the recall is 84%, which is pretty good. I'm pretty happy with that, and I output the confusion matrix as well. So we can see that it did a pretty good job classifying. We were able to classify over 3,000 for each class, with a few mistakes. So overall, I think, it did a pretty good job. The benefits of the random forest are it's pretty easy to use compared to the, neural networks. The hardest part was really processing the images and scaling them and everything. But now I'm going to hand it off to John, and he's going to talk about, the next steps.
Hi, so this is John George, part of Team Alpha, and for my portion of the malaria project, I was running logistic regression for my model. For starters, import the necessary libraries, pandas, numpy, os, to really figure out the directory. And from there, I basically created a few other directory paths where I was able to link it to the location of folders with the parasitic and uninfected images of the cells. And here we have it listed out, the lengths of both of them. And from there, we created a data frame. And in the data frame, kind of kept it similarly as Nick's. We have the images and we have labels, infected and clean. From there, also broke it out again, training and testing. With that, we had 30% testing size and a 70% training size. And moving on from that, we had to classify or be able to really figure out the dimensions of these pictures since they all were kind of different. So had to run this function here and had to do a bit of threading as well to produce the results where we basically were able to pull the minimum dimensions, the average, the median, and the max, which is listed out here. And from that information, we were able to basically get an idea of what would be like a good average across all of them, which is basically 125 by 125. And so in this area here, we changed all the dimensions of it. So all the pictures would have the same dimensions. So that way it'd be able for us to run our model with it. And we run it across. And here we see that our new dimensions are now 19,290 in terms of the training. And then we have 125 by 125 for the image size, and then 3 for color RGB. And so from here, we really wanted to normalize it. So we normalized and scaled it down. And after that, we wanted to make it smaller so it could officially fit into our model because there's too many dimensions still. And so we brought it down with the reshape, and we created, these two new sizes. But what I noticed with logistic regression is that it's actually pretty computationally heavy and takes a lot of memory. So what I ended up having to do to get it to run on my computer was I had to cut it down into 1/3 of the original sample. So this is what I did here, where I was basically looking at what 1/3 of the sample would look like. Then moving on, here is where I actually created the new variables based on our training and testing data, making it to 1/3 of the original sample. Then that's where the next is where I'm able to import logistic regression from sklearn. Then I had to fit the model with our data. And then from there, I was able to run logistic regression. And as we could see, it wasn't really the best in terms of results, with like about a 60% precision, 60% recall, and 60% F1 score. And that was through the classification report. And then what I ended up doing for the very last part is I imported a confusion matrix, and I also listed out the training accuracy and test accuracy score. And here we see, training accuracy of around 91%, pretty well. But then when we actually ran it across our testing, it was about 60%. And the confusion matrix listed here, not really the best, but it was good for us to test out logistic regression and kind of see how this model would fit with this type of classification of these images. And so with that, I'm going to pass it on to the next person.
Now that I'm recording, I'm going to introduce myself. I'm Dr. Awesome Pants the Fifth. Yes, I'm a real doctor. Yes, my name is Dr. Awesome Pants, given to me by my father, Dr. Awesome Pants the Fourth. I'm going to demonstrate my knowledge in Python and machine learning when it comes to identifying malaria pictures. Please allow me a moment to share my screen. Now, as you can see here, you have my Jupyter notebook containing my malaria machine learning algorithm. It's a fancy term for teaching a computer to learn other things about computers. So, what I've done here is I've identified all of the libraries that I need to use to perform my calculations. As you can see, there's a significant amount of notes. Don't be fooled. A lot of this is very easy to understand. As you can see, I've even included my notes talking to you. What we want to do now is explain these data sets and libraries, and that is what I will do for you over the next 2.5 more minutes. So what we have here is NumPy. NumPy allows you to organize and construct very large sets of data. We need this for when we're running analysis. And we use things like Panda, which is a library, to help us with more data manipulation and analysis. And Pill, which is actually an open source image library. All of these will help me understand what I need to do to get the job done. As you can see here, we have two different data sets. One, infected malaria cells, and two, non-infected malaria cells. We need these to ensure that our machine and its algorithm can identify which is which. This is essential. Don't mind the error. I'm still figuring it out. As you can see in this below data, this below quadrant here, I've printed and categorized infected cells with malaria and non-infected cells without malaria. Notice the title, infected. See the purple? The purple is malaria. We're trying to do away with malaria. And the bottom only shows you regular cells with no malaria. We've set these pictures up so they're the same size, so it'll be easier for our machine to learn and categorize them. This is important. Next, we must clean the data. Imagine you had 50,000 pictures, actually 500,000 pictures. Only half of them were malaria and the other half were hot dogs. You can't tell a machine to learn what malaria looks like when there's hot dogs in the way. You must avoid and discard erroneous hot dog pictures, therefore leaving only malaria. It's also important for us to ensure they're all the same size. This makes it easier for our machine to process them and not confuse it, because machines are actually quite stupid. That's why I chose to work with them. And you can see the for loop here saying that if it's a good picture, it will pass through. If it's a bad picture, it will not pass through. This is what we're looking for. And as you can see, you can use all sorts of cleaning techniques. You can drop columns, you can change data frames, you can rename columns, you can clear data, you can remove erroneous pictures so it's more accurate. No more hot dogs, only malaria. Now, we're setting variables. What these do is makes it easier for our simple minds to remember things, so when we need to use them later. And as you can see here, we've done it. We've used the same simple variables to print dimensions of our pictures. Incredible. Now, my work here is finished. Now, Dr. Jordan Yee, the 75th, given his name by Dr. Jordan Lee, the 74th, will take over and explain our random sampling and our combined data set. I will now stop sharing my screen and end my recording. Wish me luck, so I don't get malaria.
Okay, so rumors of my demise have been greatly exaggerated, but once you've created a new data set that's clean, usable, using the right format and whatever, you wanted to create a train test split of that data set using scikit-learn. You're going to split the data. Here we split it into 25% testing data and used a random state of 999. Then we use one-hot encoders for our testing labels. You can also use Keras as well. They have their own library for that as well. Then we built our models. So we imported Keras libraries, pretty much took everything that we could possibly use and downloaded it, and then created a basic model, 4 layers, each layer followed by subsequent max pool layer. And we started with 6 and increased by and doubled our filters each time. Our kernel size is 2x2, and padding is this. So, and we added some 0 padding just in case there's anything near the edges. And so our model summary looks good. We have 3,000 parameters, and we condense it continuously. And so we're going to compile it using categorical cross entropy, use the atom optimizer, and we want to judge it by the accuracy metrics. And so we're going to record our history and model.fit, use our X train and our Y train one-hot labels. We're going to start with a batch size of 210 epochs, and our validation data will be our X test and Y test one hot label. And so we run that and we get pretty good result. So 91% accuracy of our training set and 91% of our validation set. And we can further see how well this is doing by plotting it using the history that we previously recorded. And so we can see here that our accuracy has continually increased with both training and testing hand in hand, and our loss also continually decreased along the same slopes for both training and testing. But we can still go further because the curve does not seem to be flattening out. And so let's add some more layers, add another layer, add a dense layer as well. You can also add batch normalization or any other type of layer that you feel would necessarily improve your model. And so our parameters, have drastically increased, but hopefully it will produce a better result this time. And then for our compiling, we use the same compilers that we used last time. And so we run it again, and as we can see, we get a much better result this time. And so let's plot that. And as you can see, this time the graph has started to flatten out. The test and training accuracy went hand in hand, but the testing and training loss started to branch out, and the testing loss didn't seem to be improved with subsequent epochs. So we'll stop there and say that that's a pretty good model to go with. And we can confirm this by looking at our classification report, precision, recall, F1 scores, all in the high to mid 90s, and an overall accuracy of 94. That's good. And then we can also further confirm this through our ROC AUC curve. And as we can see, our AUC score is almost 1. So we're going to say that's a very good model. And so finally, now that we're satisfied with our model, we're going to save the model to our, and the weights to our computer so that we don't have to do this again. And we'll just confirm again that it's saved properly. And so now we'll turn it over to Kathleen for the reflection section.
Malaria, it's everywhere. But truly, malaria is still a big problem in many parts of the world. And with a big problem like this comes a lot of data. And that was definitely the case for our project. We had over 27,000 images, and it was obvious that we can utilize cloud computing to our advantage. And with that, we started with a virtual machine instance called Malaria, which you can see here. Following the creation of that, we copied all of the Kaggle data set through the Kaggle API right here. And we also set up a Data Lab notebook right here. Within Data Lab, we moved all of the cell images into this folder, which contains 2 folders, one of healthy cell images and one of unhealthy cell images. And as you heard previously during this presentation, we built 3 different models. The first was the logistic regression model, and that yielded pretty poor results, which was to be expected. This particular code was ran on a subset of the data set because we coded everything on our local machines first before loading it up onto Data Lab. But given that we had the power of cloud computing behind us, we ran the logistic regression model on the entire data set. And after 2 hours, we got slightly better results, but still significantly lower than what we were hoping to achieve. So that led us to our second model, the random forest model. And that was a lot closer to what we're aiming for. 0.8 was a good baseline model for us, and it was 0.8 across the board for all criteria. We could have stopped there, to be completely honest, but given the knowledge that we had on convolutional neural networks, we decided to create a model with that as well. And the convolutional neural network was the ideal model that we could have built. Around 95% across all scores, precision, recall, and accuracy were the thresholds that we were hoping to achieve. And that is very close for all criteria. So given the opportunity to experiment on this type of data set even further, we could strengthen our model by feeding it more images from outside of the data set. And that would further give it the ability to be utilized in real world situations in identifying whether cells have malaria or not. Additionally, outside data that this model can train and learn from could make it more reputable in those real life situations. So in conclusion, this is the model that we would like to move forward with for this study and this project. We thought we got pretty amazing results, and this exceeded our expectations. Thank you so much for your time, Ahmed. It's been a privilege being your student in this program, and we'll see you in the capstone project.